So the outline for this session is I'll first talk about what is linear programming, and then talk about what are objective functions, what are constraint, and how we can use these concepts to be able to solve some of the very interesting real world problems. And then we'll talk about a real world problems. We'll take an industry problem and we'll solve with R. We'll formulate the problem and we'll solve it using R, and then we'll talk about what R package is to be used, and finally we'll solve the linear programming problem using R. So what is linear programming? Well, linear programming is a mathematical technique, so that's one thing to note. This is one mathematical technique for maximizing or minimizing a linear function. Okay, and we'll see what a linear function is of several variables, okay, such as output or cost. We'll understand this definition in detail, so we'll just talk about few things that I have highlighted here. One is maximizing, the other one is minimizing. So when we talk about maximizing and minimizing, we are essentially optimizing, right? Since in a company we want to maximize profit and we want to minimize cost. So one example of it, you might have heard about linear regression. So in these regressions we have minimize the cost function. One of the major use we can relate to, because we have learned so much about linear regression and many other type of regressions. So where are we going to use this in real world? Well, we're going to use this in maximizing profits, minimizing cost, and that happens in many manufacturing companies. How much to produce, given certain constraints, and then it's also used in production planning. Pricing of products is used a lot. It's used in supply chain management. So every linear programming problem will have two things: the function to be optimized or to be either minimized or maximized, and the set of constraints. So here is an example. We have this function. So g is a linear function of several variables, x1, c2, x2, up to n number of things. Okay, so x1 and x2 are known as the decisions variables, which we want to find out. Okay, z is yet not known to us. We want to maximize z or minimize j. Okay, and c1, c2 are the constants already given to us. We know this a priori. Then we have constraints that we want to maximize g with respect to certain number of constraints, and these constraints are also in equation form. Either it is going to be equal to something or less than something, less than equal to something. That would be the case. So this is a constraint that the linear combination, a linear product of the a11 x1, a1 to x2 should be less than or equal to b1. So this is one constraint. So given this constraint, we have to maximize this. Given this second constraint, we have to maximize it. Okay, so just trying to understand what these variables are in the previous slide. Objective function, what we have seen is nothing but g that we have seen is a combination of decisions variable x. Okay, so x are decisions variable. So you just have to remember this, because these variables are to be found out from optimizations, and they are always associated with some of the cost efficient CJ, we're calling it CJ. So, and CJ, the constant values are given to us. Okay, and then we have set of m constraints which are taken into consideration while minimizing or maximizing. Okay, and we might have boundary conditions for the decisions variable, like many cases where decisions variable have to be positive. Now, another thing that I like to introduce to you, that LPP problems can be solved by using a number of techniques, mathematical tools, and one of the way that we can use is the simplex method, which is a very popular one. So here is an example. A small business sells two products. So we have got two products, we call that as product 1 and product 2. Each ton of product 1 consumes 30 working hours. Each tons of product 2 consume 20 working hours. Okay, so I've got product 1 and we have got product 2. Product 1 consumes how much hours? 30, and product 2 consumes 20 hours. The business has a maximum of 2,700 hours. So that's the maximum the business, the factory can spend in terms of in order to produce product 1 and product 2. So that's one constraint already given to, right? Constraint is nothing but a limitation or a cap on something or a limitation on something. Okay, so working hours for a period considered. As for machine hours, each ton of product 1 and 2 consumes 5 and 10 machine hours respectively. So there are 850 machines are available to us. So that's another constraint. So we have a constraint on the man hour, which is 2,700, and we have also a constraint on the machine hours, which is 850. Each ton of product 1 yields $20 million of profit, while product 2 yields $60 million of profit for each ton. So for each ton we have the profit in place, so I guess the problem is already now clear. So we are trying to, maximize profit here, right? That's the problem we have with us. For technical reasons, the firm must produce minimum 95 tons. So that's another constraint. So the minimum number of product 1 plus product 2 should ideally be 95 or more. So that's one requirement from the business side. So this is a target to be met at any cost. So that's another constraint. We need to know how many tons of product 1 and product 2 must be produced to maximize total profit. So here is what is our main agenda. So we need to maximize total profit, and the question that has been asked to us is how many number of product 1 and product 2 are to be produced to maximize profits, given the constraint that we have talked about, given the information that we have been given. Okay, so we have the constraint with us and we have a clear objective given to us that we need to maximize profit. So just tell us how many products to be manufactured, and how many of them are going to be product 1 and how many of them are going to be product 2. So the decision variable for us is the number of product 1 and number of product. X1 is the number of tons produced or sold by product 1. So that's one thing we will assume. X2 is the number of tons to be produced. Okay, so we want X1 tons to be for product 1 and X2 tons to be for product 2. The cost coefficient of these products, of these variables are 20 and 60. We have been given the profit that is made from product 1 is $20 million and it's $60 million from product 2. So the cost coefficients are 20 and 60. Remember C1 and C2 we talked about in the definition. That's exactly what it is. Therefore, the objective function is defined multiplying each of these variables and its corresponding coefficient. So objective function, if we is defined as G, is equal to 20x1 plus 60x2. We have several constraints. We have working hours constraint, and the total number of working hours used for product 1 and product 2 is equal to 30x plus 20x, 30x1 plus 20x2. Has to be less than 2,700 hours. Okay, so how do we come up with 30 and 20? Well, 30 hours is taken for one product, right? And 20 hours is taken for product 2. Similarly, for the man hours, we'll just use the same equation, same way of formulating. Well, we have 5 hours taken for product 1 and 10 hours taken for product 2, and that summation, product sum product, should be less than 850 because that's the maximum available to us. Total units to be produced should be should be greater than or equal to 95. So x1 plus x2, the sum of x1 and x2 should be greater than 95. So that's the third constraint. So we have this problem in place. We have to maximize profit, and the profit function is 20x plus 60x2. x1 and x2 are the decision variables. Decisions variables are the variables to be found out from optimization. So we want to know what exactly is the value of x1 and x2. We want to know the actual values, right? And we have constraint. Now in order to solve this in R, we'll be needing a package called LP solve.